So welcome everybody to another GOAP webinar. My name is Mitchell Lyons, and today we're going to be talking about seagrass mapping. There is a Q&A functionality here, and at the end of the talk we'll go back to that. So please put your questions in there, and there'll be plenty of time at the end for us to go over that. Okay, cool. All right, so quickly, a little bit about me. As I said, my name is Mitchell. I'm part of the Centre for Sustainable Development Reform, which is where the GOAP Secretariat is hosted at UNSW. Hopefully you're wondering now why there's pictures of cows on the screen. Has nothing to do with seagrass mapping, just a quick little chance to reset our brains if we've jumped on this from somewhere else, had a busy day or just starting our day. The reason I have this photo up is that I live on a little farm down south of Canberra on Narrego country in the Snowy Mountains. So what are we going to cover today in terms of seagrass mapping? It's fairly broad, and like I said, we're recording this session, and so any of the bits and pieces that we miss or you want to go back to, you can definitely do that. We're going to go a little bit through the rationale of why we even want to use remote sensing or Earth observation for seagrass mapping or for any kind of coastal ecosystem monitoring. And then we'll dive into a little bit about the methods. Not really technical, but enough so we kind of have background for the things we're talking about. And then we'll go through some examples of extent and a bit of condition mapping, how this ties into time series monitoring and what are kind of and how this is a precursor for the next steps of going into ecosystem services. We're not going to talk a lot today about actually constructing accounts from the seagrass mapping or constructing the ecosystem services estimates. This is really about like the options and methods we are going to potentially want to use for characterizing seagrass in the first place. So let's talk a bit about rationale. There's kind of a couple key pieces of rationale for why we take Earth observation approaches, and some of these are obvious depending on what field you're coming from, and some of these might be less obvious. So this is a good example of one of the core motivations for remote sensing. This is a beautiful picture of Arnhem Land up in the northern part of Australia, where we have a mix of seagrass, coral, and other environments, mangroves. And one of the key reasons we might want to use remote sensing is because these are really critical ecosystems, but they're really hard to get to and hard to monitor frequently. Driving here is a really big mission, and you can maybe fly in or you know, sail a boat in there too. But one of the big motivations for using remote sensing is obviously the access in remote environments to get a picture of what's going on regularly. One of the other big motivations for using remote sensing um, is to be able to look at the same place or the same thing repeated over time. And so this is an example in South Korea. This is back in 1991 from a Landsat image, one of the first kind of mainstream Earth observation satellites to be producing archives of satellite imagery. Um, this is an area in South Korea in 1991, and then we look at the same area in 2008. Um, and this is the other kind of main reason that we talk about wanting to implement a remote sensing or Earth observation framework when we start to think about not just environmental monitoring, but specifically when we think about implementing accounts. Because we can see here, obviously, that those intertidal flats have been reclaimed to have the Incheon Airport, which was kind of built in phases from 1990s like through to 2000s. So that is to say that generally speaking, that we're moving towards having spatial information frameworks as the underlying data set for the way we do ecosystem and biodiversity monitoring throughout the world. And so this includes mapping, like we're going to be talking today, but then the upstream applications of that, which are our monitoring frameworks, accounting, planning, and then also the evidence for the types of policies we implement, or the types of things we do to change policy to better adapt to new management or monitoring frameworks. So it's nice to have repeatable and transparent frameworks to do these, and that's really the core of the Earth observation. And so when we talk specifically about a mapping framework, ecosystem extent maps are kind of the really the underlying base piece of information that we use to start constructing accounts. Um, and from within those ecosystem extent snapshots, for ecosystem accounting anyway, we build our information up on top of those, on top of that, to construct all of our downstream things, like whether it's just opening and closing accounts or whether it's things like ecosystem services and the benefits that flow through to different parts. So, um, ideally, we're going to have a mapping framework that has kind of flexible structures for the types of data that go in and the types of mapping products that come out. So today we're going to talk about kind of modern machine learning based frameworks, specifically in context of seagrass mapping, which is kind of one of those, I guess seagrass mapping is one of the emerging gaps in the kind of coastal marine mapping space, building on from kind of pretty solid approaches for mangroves and other kind of shallow um, near coastal environments. So we're not going to go into to a lot of detail today on the actual technical parts of the pipeline, but I did want to go over some basic concepts so we can understand the types of the examples that we're going to talk about, but also so we can understand what the kind of constraints and limitations and where resources and investments required to get the kind of products that we need. So we'll go through kind of these kind of four key parts of a modern kind of machine learning pipeline. So the underlying pillar, I guess, of all modern kind of machine learning processes, whether they're kind of fairly basic, well-known machine learning, all the way through to really kind of cutting edge architecture, um, is the training data that goes into the framework, and training data are kind of used to encompass the training data for fitting and building models and maps, as well as the data that you use to kind of provide validation information about how good the product is, how variable it is, and things like that. So there's lots of different ways you can get training data. Uh, all it really is a confirmed occurrence of something that you're trying to map. So in this case, it would be a confirmed occurrence of seagrass at a specific location and time, and then more properties about it. So like how much seagrass was there, maybe what species, or even things like how much carbon was in the roots of the species at the time. So there's a bunch of different ways we can get it. There's the classic fieldwork approach, where you're diving or snorkeling or swimming, or even if you can see in that photo, there's a dog helping out in this particular one. Um, so that's one way. It's a pretty classic kind of standard way of geolocated stuff. Drones are kind of increasingly being used as a way of collecting field data, or training data for models. And drones are nice because they can cover a lot more area, and with increasing detail and information. So there's a really cool image of a multispectral drone there that we flew in Vanuatu on Pele Island recently, and you can see that it not only captures this kind of nice visible, what you're used to as a photo on the bottom right there of that mosaic, but it also captures information in a bunch of other bands through from kind of ultraviolet through to near infrared. And so we can use that to figure out occurrences of things like seagrass that we're interested in making training data for. Image interpretation is another really common place. Like one of when we first started the talk talking about motivation of some places are really remote and you simply can't get to them often enough to get really good long time series of information about how to do mapping. And so we rely on high resolution data or time series of information to estimate where things might be so we can use those to help train models. So that's training data. And the next thing that we want to think about is, okay, we've got training data, which is confirmed occurrences of what we're interested in. So in this case, it's seagrass. What we want to do now is start to think about building a model to predict where that seagrass might be or what type of seagrass it might be or whatever it happens to be elsewhere in the environment. And that's so into the rest of the environment, which we I've termed here predictor layers, but you might have heard them as kind of model covariates, or there's a few different bit of terminology for it. But essentially, we're trying to build a stack of information about about stuff that might be important for figuring out if seagrass is there or not. And then so there's a few different classes of information that we might want to put into a model. Now, in a classic kind of remote sensing framework, this was mostly image data. And so whether that was from a plane or from a satellite, that's our kind of classic, Landsat or Sentinel-2 type mapping frameworks. And then of course, more recently, there's from the early 2000s onwards, we've of course had a lot more high resolution sensors, like all of our kind of worldview, planet, our Airbus kind of varieties of satellites, which, now give us information down to kind of, 15, 20 centimeter pixels. Um, there's varying spatial and temporal resolution for these things through from really coarse scale daily things like MODIS, so they're like 1 kilometer or 500 meter pixels, but we get kind of twice daily information about what's there, all the way through to like really high resolution satellites that might be able to give us an image every 1 or 2 weeks or something like that. Um, And there's a lot of different ways that we get the data these days. There's a lot more kind of what we term analysis ready data or ARD. So it's much easier for us to touch that data set. So that's kind of our classic visible information that we would think about in a remote sensing context. But more and more so these days, we actually start to include a lot more things into our models. One of the classic things we tend to include in a nearshore shallow coastal environment for mapping things like seagrass and reefs and the edge of mangroves is kind of elevation and depth bathymetry layers. So one of the really common things we would try to do now is get bathymetry data to include in seagrass models and we can start to use it as a surrogate for things like light availability. And also we might make other derived variables like slope. So that might be slope on the land for a land-based thing, but particularly when we're talking about seagrass, slope underwater is really important because it's a really good indicator for really steep environments underwater or things that are more hydrodynamically active, um, are less likely to be growing seagrass or at least certain types of seagrass. One of the bigger changes too in kind of recent in recent more modern kind of machine learning or particularly cloud-based Earth observation frameworks is the ability to kind of move away from kind of single date spectral information. So this is a good example here. So let's take this kind of Gulf area here. This is an image on a particular day. So in a lot of the world, and particularly in tropical parts of the world, you have a lot of cloud cover for a lot of the year. And so one of the things that we start to have implemented and really has almost become the standard now in the way that we try to implement at least large scale mapping processes is to combine lots of imagery together and then do some kind of selection of process across pixels. So you can see in that previous example, it was full of cloud, but then say we take a stack of some time period. That could be a really long period if you wanted to get a really good baseline of what's there on how variable the pixel is. Or it could be quite a short period of say 3 or 4 months or 6 months or something like that that aligns with maybe a field campaign that you've done. And so across that, you stack all those images up together, and then you can make a distribution for that individual pixel. And you could do something like, say, choose the best one there, or choose a median, or choose some percentile that you think best represents a cloud-free kind of thing and make an image. But also really and commonly what we would do now too is take the percentiles of that pixel stack distribution and then use all of those percentiles as part of the predictor layer for that modeling. And more too, you'll now start to see this kind of concept of embeddings or kind of composite layers that have been used in like either foundation models or some kind of more, I guess, kind of deep learning architecture where we have multiple different sources of not just spectral, but also other information embedded into these kind of layers that are ready for us to use for modeling or mapping. So we've got our training data, which is where we know the thing is we're interested in. So in this case, seagrass. We've got a big stack of data that we think are important for telling us whether seagrass should be there or not, or what type of it is, or how often it is there, or how often it's not there. So now we have to think about, okay, we've got to choose some kind of model, some kind of model to let us predict out into all the places where we haven't been, or we want to estimate or make a map for. So there's a few different kind of options here when we start to think about what kind of model we want to fit, which is usually dependent on um, our goals, but also what type of training data we've collected and also what type of predictor layers we've been able to compile. And so occurrence is the very first thing that comes to mind. So we're thinking about extent. So it could be, what it is. Um, then I guess we want to figure out within that if there's particular subsets. So an example might be it's a coastal wetland and within there it's seagrass, or an example might be it's seagrass and then within there it's a particular species or a particular cover. And then there's also from year to year we will think about modeling or mapping change. And so there's different ways of doing that. You can infer change by the extent that they're each year, or you could say map change specifically to see if pixels have changed, and then try to map the type on top of that. So they're the kind of types of information we want on a map. We also have to choose an architecture. And so what I mean by that is like choose whether we use kind of a fairly like kind of robust, well understood, supervised model, like say like a random forest or gradient boosting, something like that, all the way through to like really modern cutting edge deep learning methodologies. And again, what you're able to implement within there is really dependent on the training data. So if you have just lots of points where stuff is, you're probably going to be limited to some kind of supervised machine learning method that's classic and robust, like a random forest or gradient boost. But if you've got really good, say like good drone coverage where you've annotated a lot of information about the environment for your training data, then you can probably going to be able to use that to do some kind of neural network or deep learning algorithm. Again, we don't need to go into the full details of all this, but it is good to know that the types of models you're able to fit are really dependent on the types of training data and input layers that you generate. So hopefully we've decided what we're going to do. We fit some models and we get to this point where we have some information about the extent or the probability of occurrence, or the coverage or the species of our seagrass or something. And maybe we have that in a time series context. So we've kind of gone through this kind of analysis pipeline and we have products. So we're going to stop there in terms of the technical kind of side of like where we're at with seagrass mapping. And now we're going to work through, I guess, a number of different examples at different scales to show some of the things that you might expect to see or be able to plan to implement at various things. So we're actually going to start at the opposite end of scale from local. When we say kind of, I think that the talk said local to global. We're actually going to probably flick around the other way because um, it gives us good context for the resolution and the type of information and the limitations for different things. So we're starting with this first example of, so this concept of global mapping products. And it could be any kind of global mapping product. Like there's in this particular example is the Allen Coral Atlas, where we've got a seagrass class within the benthic habitat product. But we would be familiar with a bunch of different global products like the Atlas, Global Mangrove Watch. There's kind of some emerging seagrass products that are coming too in this context. And there's also obviously some historical products for other coral reef or seagrass products historically. Um, One of the challenges, of course, with global products is some ecosystems are characterized well and some are not. And even within ecosystems, like seagrass is a good example here. from the Allen Coral Atlas example, in the Bahamas and Cuba, where they're really tightly associated with the kind of shallow coral reef environments. The amount of seagrass area is really well characterized, but for example, in Indonesia and Australia, where there's a lot of complex seagrass environments that are very disjointed from coral reef ecosystems, often we have really poor coverage of the seagrass area itself. And so one of the things I was talking about earlier in terms of developing a mapping framework from the very beginning that is able to deal with flexible input and output structures, it enables you to kind of to modify products a bit on the fly depending on what you have. Um, I've chosen this specific kind of sequence of example products because it's ones that I've worked on, but you may be thinking in your head, this is analogous to some other product that you've either worked on or have used in your particular jurisdiction. I'm using this sequence because the underlying digital infrastructure that makes these maps is pretty consistent between all these methods. It's just a matter of the kind of input data and the covariate stacks and the actual place that it's been deployed is a bit different. So we've seen in that previous example, we've got a global product. It does some things good, some things not so good. This is an example in Vanuatu where you can see on the left there, the Allen Coral Atlas product. And this is a really good example of seagrass being missed in a coral reef environment. So according to that product, if you were using it, you would see that you would think that that's all kind of coral in that kind of red environment that you see. We know this to obviously not be the case, but based on a smaller scale or local scale project, we've got some mangrove information there too, which is pretty good. And so what we've done here is used a really similar mapping framework that we use to do the coral mapping, except that we've pulled out the seagrass component of the model and we've fit an individual probability model for seagrass with a bit of extra local training data. So pulled new training data points, expanded them, made a new model just for this area in Vanuatu, and we fit a new model. So now you can see on the left there, that's a model of seagrass probability of occurrence. And so when we choose an appropriate threshold there, we can combine all of those individual products now, the mangrove, the original coral stuff, plus our new seagrass product. And we now have a product here which is kind of ready to start doing kind of at least our extent component of the accounts. So this is a really good example of why if you implement a flexible mapping framework from the beginning, it's quite easy to turn some dials. And this is a similar process that we've implemented in multiple locations where we take the the mapping framework that we've used for other things, pull either individual ecosystems or combinations of ecosystems out, add new training data and sometimes new image data stacks, but again within that same digital infrastructure to make new products. Um, so this is another example of the same seagrass probability model that we just saw for the Vanuatu example. This is an example in Maldives on Lamu Atoll, and we had some again some new training data, some new image data. We made kind of much more temporally constrained stacks compared to say the original Atlas product. And we've fit and done seagrass maps for 7 different time periods. So from 2018 to 2024. And so now we can start to think about, at least for seagrass itself, to think about how we might start to construct accounts in terms of change over time as well as opening and closing. And again, this is kind of that first step towards constructing some of those downstream products like ecosystem services. Yeah. So again, this is the really very similar model architecture, cloud-based implementation as the previous 3 examples we've seen, but we've just again modified them. So the next example I want to show is how we might move towards kind of a, a more nationalized or jurisdiction-based kind of implementation of a mapping framework that includes seagrass, but how it kind of probably has to sit within a larger kind of effort. Um, so this particular example is how we've taken that same kind of that same framework and architecture for fitting the products that we've just looked at, and moving that over to a new tech stack, essentially. So moving away from kind of a research-based infrastructure. So the stuff you've seen thus far in examples was all done on Google Earth Engine. And so one of the challenges, I guess, for when we start to think about implementing infrastructure at a national scale is we want some capacity for it to be sovereign infrastructure. And so this is a bit of I guess there's a timeline. I've kind of included some information here on this example about timelines and also governance on how you actually set these kind of projects up. So really this particular product I'm about to show you and explain a bit about is really motivated by accounts. And and um, and I guess that idea of implementing sovereign infrastructure. So again, this is still a fully cloud-based workflow, but implemented on in Python and Open Data Cube instead of Google Earth Engine. So lots of different training data sources through. Again, the actual tech process is not, I guess, super important in this context. But it's just saying that we've done the same type of training data, same type of covariate data stack, same types of models, but just flicked around a little bit with the tech stack on how it's implemented. So this particular product is a Sentinel-2 based product. It's at 10 meters. And importantly, it's kind of an annual product now, so it will kind of be the I guess the main input into the ecosystem accounting, at least the ecosystem component of the national accounts going forward. And I did want to make just a quick point here on governance in the sense of if we are thinking about implementing ocean accounts at a large scale, especially at a national jurisdiction scale, you need to start thinking about how the governance works in terms of different agencies together. Australia is kind of a good example of a really complex, a wide range of environments, complex ecosystems, but also complex in terms of implementing the digital side of the mapping infrastructure. So we have environment agencies which drive it and fund it. We have a geoscience agency which handles the technical hosting of the infrastructure, the publishing of the actual accounts themselves, and the compilation of the accounts is by the Bureau of Statistics. And along the way, universities like ourselves, as well as other government agencies like CSIRO have helped. So that's kind of all been fairly focused on, I guess, extent so far. And really, I guess, for the frontier of seagrass mapping is it is where to go to next in terms of what you need in terms of quantifying ecosystem services if we're going to that next stage of compiling ocean accounts particularly. And it's kind of obvious, but it's the same as if you're thinking about mangroves or salt marsh or anything like that. That condition is really important for starting to figure out what some of those services might be. I mean, carbon is a really good and common example, but there's plenty of others too, like our fish recruitment, coastal protection, water quality, all those kinds of things. And this is really where I guess the frontier of seagrass mapping is. So I want to show an example that is on a fairly small area. And I guess that's why I wanted to explain a little bit in the beginning about the types of training data that goes into a model. To get information about seagrass condition, we need information like that going into our model in the first place. So you can kind of see it's a fairly small photo, but up on the right, this one kind of small island area has had quite a lot of information gone into the modeling. This particular example, you can see that a combination of seagrass as well as sand and macroalgae has been mapped. So we're kind of making a bit of I guess, a fractional cover product for seagrass. which is really good information if we're trying to derive services like coastal protection, or fish recruitment grounds, or things related to hydrodynamic flow. On the right, you can see an example of the cover level of seagrass itself, in different there's a few different species as well. And so obviously then seagrass cover is a really good surrogate for, how much above and below ground biomass there might be. And so again, this particular example is again the same underlying kind of digital infrastructure as we've just seen, except we're turning the knobs on the type of data that's gone in and the type of model that's been fit. So we try to keep that as consistent and as flexible as possible. So, just before we finish up, too, it's I've showed a set of examples today, I guess, that have had a theme on particular applications that I've personally been involved with, and had helped implement the infrastructure. But hopefully, you'll be able to think of analogies to various other jurisdictions. A really good example of condition. I didn't want to steal the limelight or anything, but if you have time, go and have a read up on Indonesia's national seagrass mapping project at present. They're doing a really, really good job, and probably one of I guess probably the forefront in the world at the moment on kind of really large scale condition mapping for seagrass. And so, throughout 2026, I'm sure we'll all see more about that. Um, Two links I wanted to share here. Um, the first one, and you should either can get it, we'll either post it in or you can get it from the slides later. All of the examples I showed today are really well characterized in an SOP for seagrass mapping that we've developed. It has a SOP for the different types of seagrass mapping, as well as a specific example, which has some fully worked examples and data sets for doing extent and condition mapping. That last slide you saw on the fractional cover, and some species stuff as well. And if you did want to get more into thinking about some of the cloud-based methods for actually implementing it, there's also a nice little tutorial and some exercises to do on that link as well. So that was um, everything that I wanted to cover today. We will let me just stop sharing so I can see if there's been some questions and stuff put through. Let me just have a look. There is one question so far. Are there any global data available online accessible? I'm not sure if everyone can see the Q&A, so I'll just read it out. Are there any global data available online accessible for the Indian Ocean and the Red Sea, or specifically for Somalia? There's not many good global data sets available for seagrass at present. Some places are good in the Allen Coral Atlas. Others are quite poor, as I'm explaining one of those slides. There there are upcoming global products that are kind of going through that kind of tech uplift phase. So in the coming in 2026 onwards, we'll start to see probably more global scale products, but but it always comes with the caveat that global scale products are always going to be quite difficult for seagrass just because of the nature of it being subtidal and so variable in its ability to be mapped, and also so variable in its ability to have had good training data collected. And so really for from an ocean accounting perspective, individual jurisdictions are probably always going to have some kind of program for at least retraining or tuning kind of their seagrass models. It's going to be quite a while before we have that level of information like we do, say, for like Global Mangrove Watch in a kind of subtidal marine environment, unfortunately. Oops. That's If there's any other questions, yeah, you can put them in the Q&A. Um, um, Another one here from Ken, which is to discuss how temporal variation in imagery at different scales can be considered, tides and rainfall. That's a really good question, and there's a few different ways to think about variation. One of the first key things whenever we're thinking about implementing kind of seagrass mapping in a particular location is to kind of think about what the life history stages are like for seagrass. So you have I guess if we could maybe split it into three kind of simplified ones, which is like the ephemeral species, which are either colonizing or they tend to go with seasonal, availability of the various biophysical needs. Some of the species that are like kind of reasonably persistent, but might change on a kind of 2, 3, 4 year cycle, versus those persistent species which are there for hopefully long term. And then, so the implication is that for those ephemeral species, you expect to see quite a lot of variation, and disturbance might not necessarily be such a bad thing. And those really persistent seagrass beds, if you do see disturbance, then that's a bad thing, for example. So one of the reasons, and I touched on it really quickly, is fine-tuning the predictor covariate stack for the type of seagrass you're trying to monitor. And one of the things that we've found to be really effective is for if you're okay with kind of mapping at that Sentinel-2 10-meter pixel scale, using those multiple month or even multiple year covariate stacks to your advantage, and use some of those percentile metrics in the stack. And so we've had really good success on differentiating, I guess, those colonizing versus persistent species by having, 10 or 20 percentiles. So say for a Sentinel-2 period for 6 months for a particular pixel, we include for all of the bands the 10th, the 15th, the 20th, or maybe depending on your particular scenario, it could be like the 20th, the 40th, the 60th, and 80th percentile. And that gives you information not just about what the pixel looks like on average, but across the seasons, like what its maximum and what its upper and lower limits might be. And that can help you sometimes distinguish between particularly those lower cover things. In terms of like the more biophysical implication of temporal variation, um, tides and tide height is a really can be in some environments a really important factor. So one thing for the last two examples that I showed, part of the predictor stack that we used were actually low and high tide composites. And so what we would do is before putting the predictor stack variables into the model, we actually tag all the individual image acquisitions with their title stage, which requires you to fit a title model. And there's local and global scale title models that you can use to tag imagery. So what we said is for one particular year, say 2021, for all of the Sentinel-2 scenes that captured on that year, we'll tag them with low tide or high tide. And then we kind of split those two sets of covariates out and use maybe just the low tide covariates for one project might be what you want, and maybe for another project you might want high tide. And one of the other, like, I guess the final thing to consider is that because of the sun synchronous nature of most of the satellites that are capturing, they tend to not capture the full tidal cycle for most ecosystems. So you're kind of looking at kind of an observed tidal regime rather than the true full one. So we've got another one about the depth limit. So the depth limit is a really good natural question for seagrass. In a general sense, that varies quite a lot depending on where you are in the world. In that last example I showed with condition, that was a really nice example and a really optimum environment for mapping seagrass. The water's cool and um, most of the time really low turbidity. And so we were mapping pretty effectively seagrass down to 35, 40 meters deep, um, particularly in some of the areas where there wasn't too much mixture on the bottom with other with other macrophytes or algae or things like that. Um, but in some areas, particularly in either tropical areas with really high river flows or really high tidal range areas with a lot of tidal resuspension of sediments, you on a particular day, the limit for mapping seagrass might be, half a meter deep because that's the optical depth on that day. But again, one of the motivations of moving over to this paradigm of mapping via multi-temporal composites and stacks is that we try to remove the influence of optical depth as much as possible. And so one of the things that we've found really effective for, I guess, maximizing the depth at which we can map seagrass is to use probably a lower, often in really turbid environments, use a lower percentile for a stack. And for example, maybe like over a 6 month or a 1 year period, maybe the 20 or 30th percentile is actually the better in a better metric for thinking about the best optical clarity that you might have been able to detect seagrass at. So it's a complex question, but in general, you could probably say something like, in most places in the world, you should be able to across a temporal stack, be able to see seagrass down to 15 or 20 meters. But again, really dependent on the data that goes into the modeling. So your training data is really important to be able to make sure you've got a nice spread of not just a spread of depth ranges, but a spread of different cover types of seagrass from low cover to high cover, as well as different morphologies or species ideally. So like different leaf shapes and different leaf orientations and things like that. Um, Last question here is just come up. The Ministry of Fisheries and Blue Economy of Somalia and Marine Environmental Research are yet struggling to collect critical habitat data. And what a cheap and suitable methodology for tools for collecting. In terms of the training data itself that goes into models, probably the most cost effective these days is to utilize some kind of if you want to have in-field data, one of the most cost-effective ways is to collect field photos, have them geolocated, and then use some kind of machine learning pro platform um, to to quantify what's in those photos, and that's a really good way of getting lots of information really quickly about what there. So what I mean by that is you say take a bunch of photos, have them geotagged, upload them to a service that quantifies if there's seagrass in the photo or not, and that kind of generates your training data set. And in terms of being accessible image data sets, a sensor like Sentinel-2 now is probably the entry point for most large scale or more cost-effective mapping programs because the imagery itself is open source. It's really widely used. It's on all of the main cloud provider platforms. There's for Sentinel-2, there's Earth Engine, there's AWS, there's Planetary Computer. They all have touch points for these data and pretty well characterized methodologies for it. A lot of places are also moving over towards having, these curated data sets where there's a combination of maybe drone flights with, pretty affordable platforms these days, as well as some interpretation for things. But really, it's about getting a program up that has the ability to store and curate training data information, and then as well as have this kind of digital infrastructure that lives on. Um, and one of the advantages of having cloud-based is that it's all kind of stored as all the infrastructure itself for making maps is stored as code, and online rather than having like a really big backlog of data and data sets sitting on computers. But it's a really hard question to answer because it's quite specific to the application. Um, so one thing just pop up. Um, the Yeah, I mean we can in terms of like specific guidance on software and implementations. Um, I tend to advocate for kind of open source platforms. So whether that's a right from the very beginning on your desktop and based environments from things like QGIS, um, all the way through to implementing mapping programs themselves with Python or Earth Engine, those kind of platforms that are all open access. It reduces the initial cost burden, of course, but it also allows you to get much better input from different people. We've found it's been much easier to collaborate and help get programs up and running if they're already implemented in open source software because we can dive straight in. Um, but yeah, any really specific question, you can feel free to reach out to me or others at any time. Um, Definitely have a look at that. If we will send around, all those links are up there. Definitely have a look at the SOP and particular examples. They include the code itself that you might want to start thinking about running in Earth Engine. And if there's any other specific parts of code that you want to get access to and you can't find, then just hit one of us up. Pretty all of the examples that I showed today are completely open source in terms of the code that produces them. So very happy to redirect there if you can. And yeah, in the chat now, my email and others' emails are in there. So if there's last chance for questions. Um, oh yeah, just and quickly in that last question there. Yes, in that SOP, it has intertitle and subtitle kind of portions to it. It doesn't specifically focus on inter or subtitle seagrass. It's specific on the infrastructure itself, and you could substitute in different covariate data stacks and training data, or even combine different ecosystems in there. It's quite flexible. Maybe we'll give one last minute. But if not, thanks for joining today. I hope you found it useful, and I hope encouraged and inspired some more effort into seagrass mapping. And as mentioned, feel free to reach out to me at any time or anyone at GOAP in terms of integrating seagrass into ocean accounts.